Hello and welcome. Today, we're diving into a really fascinating glitch in one of the most powerful tools for predicting human behavior. We're talking about game theory, and the brilliant fix that makes it smarter, more accurate, and honestly, a whole lot more human.
So, let me ask you this. Can you mathematically predict what someone's going to do next? Whether it's a high-stakes business deal, a chess match, or even just figuring out where to go for dinner. For decades, this was the promise of a very specific field of study.
And that promise came from what we call standard game theory. It was built on this really elegant idea of the perfect player. It basically assumes that all of us are like supercomputers, perfectly rational, always thinking 10 steps ahead, and always choosing the absolute best move. It's a beautiful system on paper, but it has one tiny, fatal flaw.
Yeah, there's a glitch, because the moment you pit this model against real, messy, unpredictable people, it just breaks. The predictions don't match up with what people actually do. So where did the theory go so wrong?
Well, it turns out the problem isn't the math. It's the assumption about us. And this is where behavioral game theory comes in. It scraps the whole perfect rationality idea for something called bounded rationality, which is just a fancy way of saying, hey, we're human, we're not perfect. So instead of just pure logic, it uses real experiments and data to figure out how we actually behave. The goal here isn't to find some perfect theoretical answer, it's to predict reality.
So what we're talking about is a huge upgrade, a more human game theory, and it's guided by three really important principles: being precise, being general enough to apply to lots of situations, and being disciplined about sticking to what the real-world data tells us.
And here's the crucial insight. The problem was never the game itself, but our own limited mental bandwidth. Standard theory just kind of pretends this limit doesn't exist, but this new model puts it front and center.
And this is where it gets really clever, with this model of thinking steps. Okay, think of it like a set of Russian nesting dolls. At the very center, you've got your level 0 thinkers. These guys aren't really strategizing at all. Maybe they're confused, or maybe they're just picking at random. Now, one level up, you have level 1 thinkers. They assume everyone else is a level 0, and they play their best possible move against that randomness. And then you've got level 2 thinkers, who are one step ahead again. They assume everyone else is a level 1 player, and so on. It just shows that we all have different levels of strategic depth.
Now, here's the really elegant part. We don't actually need to know every single person's individual thinking level. We can describe an entire population with just one number. That number is called tau, and you can think of it as a rationality dial for the whole group.
This chart shows you exactly how that dial works. So, on the left, you see a group with a low tau. That means it's mostly made up of level 0 and level 1 thinkers. But then you look at the right with a high tau, and that population is way more strategically sophisticated, with more level 2 and level 3 thinkers. It's amazing how this one single number can capture so much about a group's behavior.
Okay, so this all sounds really great in theory, right? But here's the real question. Does it actually work in practice? Does this thinking steps model really predict what people do better than the old way? Let's take a look at the data.
All right, so this table puts the thinking steps model head-to-head with a standard one. The number you're looking at is the mean square deviation. That's basically just an error score. And just like in golf, a lower score is better. And would you look at that? The thinking steps model's error rate is less than half of the standard models. That means its predictions are way closer to what people actually did.
This model is especially powerful in a classic experiment called a market entry game. The setup is simple. Imagine a group of people, and they all have to decide whether or not to enter a market. The catch is, the market can only support, say, 5 competitors. If more than 5 people enter, everybody who entered loses. But if 5 or fewer get in, they all win. So, how do you coordinate when you can't talk to each other?
Well, the results are so incredible, so orderly, that the Nobel Prize winner Daniel Kahneman once said, "It looks like magic." People just seem to know what to do. But the thinking steps model shows us it's not magic at all. It's the totally predictable outcome when you have a population with a natural mix of level 0, 1, and 2 thinkers. Their collective behavior just naturally avoids overcrowding the market. It's pretty amazing.
But thinking is only half the story, isn't it? We also learn from our experiences. And that's the second major upgrade in behavioral game theory, a model of how we learn. And it's based on a very human feeling: regret.
It's this concept of foregone payoffs.
See, we don't just learn from the $10 we won. We learn even more from seeing that if we'd made a different choice, we could have won $100. That foregone $100, it stings. And you better believe that's going to change how you play the next round.
Okay, so we have this incredible new model. It accounts for our limited thinking and how we learn from regret. It works beautifully in lab experiments, but why does any of this matter in the real world? What can we actually do with a more human game theory?
Well, the applications are huge. This can help us explain things like financial bubbles, where some traders might just be thinking a few more steps ahead than everyone else. It can also be used to design way more effective contracts and incentives for employees, because it's actually based on how people really think and learn. The list goes on and on.
So the main takeaway here is pretty simple. When we let go of that old, flawed idea of the perfectly rational player and instead build a model based on how our minds actually work, with all our cognitive limits and our tendency to learn from what if, we end up with a game theory that's not just more accurate, it's profoundly more useful.
And that leaves us with one last, kind of mind-bending thought. If we can create a mathematical model that accurately predicts so-called irrational behavior, then is that behavior really irrational at all? Thanks so much for joining me.